Diastereomers. Enantiomers are stereoisomers that are non-superimposable mirror image. Normally, when a molecule has one chiral carbon atom, they have two stereoisomers. They are termed or called enantiomers. Normally, the chiral carbon atom is a carbon atom that has four different groups attached to that carbon atom. And then we can have one of two possible configuration depending on the arrangement or the order of the different groups as we give them priority. So they can be either S configuration or R configuration. So if we have a chiral molecule like this one, it has one chiral center here. The first one is R configuration R, the second one is S configuration. These two are mirror image to each other and they are not superimposable. They are called enantiomers. These two molecules, both of them are S configuration, so they are the same molecule, they are not different, and they are not enantiomers. The enantiomers have identical chemical and physical properties. They only differ in their rotation of the plane polarized light. So their rotation to plane polarized light is equal but in opposite direction, and this is the only difference between enantiomers. So what are diastereomers? When a molecule has two chiral carbon atoms, they can exist as three or four different stereoisomers. The stereoisomers are the stereoisomers which are not enantiomers. So not all of these will be enantiomers. We will have the stereoisomers and we will have enantiomers. So let's have a look at this as an example. So we have ephedrine here. It has two chiral carbon atoms. The first one and the second carbon. These are two chiral carbons. And we have four possible stereoisomers here based on the different combination of configuration at both carbon atoms. So the first two will be the one which has R configuration on the first and second carbon atom. The second one is going to have the S configuration as the first and second carbon atom, and then we could have the R configuration for the first and S for the second, or the S configuration and R configuration for the second. So we have four different possible stereoisomers. Now the enantiomers will have to have a complete opposite configuration of both carbon atoms. So R and R will be the enantiomer of the S and S stereoisomer. However, if only one of the two has changed, they are not going to be enantiomers. Also, when we have the R at the first one, S for the second carbon, then when we change the first into an S and the second into an R, so opposite configuration of both, these are going to be enantiomers. If only one of these changes and the other doesn't, these are called diastereomers. So if we have a look at this stereoisomer, which is the RR, then the one opposite to it, which has one R and one S, is the stereomer to that stereoisomer, because only one configuration has changed. Also, the one with S and R, this one at the bottom, will be the stereomer to this one because only one has changed. And you can apply the rule for all the different stereoisomers. So what is the difference between enantiomers and diastereomers? Enantiomers have identical chemical and physical properties in an achiral environment. However, diastereomers, they have different chemical and physical properties, things like melting point, boiling point, solubility, and so on. These are different. So if we have a look at the different enantiomer and diastereomers of ephedrine, you're going to see that the RR and SS, which are the enantiomers, they have the exact same melting point range, and however, they only rotate optical plane polarized light into opposite direction but the same value, so minus 52 for the first one and plus 52 for the second one. While the diastereomers like the RR and the RS, they have completely different melting point range, where the RR is 117, 118 and the RS is between 40 and 41, and the optical rotation is also different. For the first one is minus 52, the second one is minus 6.3. while the RS and the SR, which are two enantiomers, they have similar or exact same physical properties, the same rotation of plane over polarized light, but in opposite direction. So for to convert between enantiomers, both chiral carbon atoms must change their configuration, and all stereo centers must be different for molecules to be enantiomers. So now when we have the two ephedrine, the RR and SS are enantiomers, the RS and SR are enantiomers. For to convert between the stereomers, only one carbon has to change its configuration while the second one has to stay the same. So RR will be the stereomer with RS and with SR, while the SS will be also the stereomer with the RS and SR and so on.